Good morning, everyone, and welcome to EDP and Applied Mathematics Seminar. It's a pleasure for me to open session 89 this seminar. Today we have two excellent speakers, Victorita Dolean-Maini and excelente. Introducing Victorita Dolean-Maini, we have the Professor Anna Dubova. Thank you, Anna. You can start.
Okay, thank you very much, Juan. Good afternoon, everyone. So it's a great pleasure for me to present Professor Dolean. He just joined the Eindhoven University of Technology as a full professor in scientific computing. Before that, she was a part-time professor at the University of Strathclyde in Glasgow, where she still holds an honorary position. She's also a fellow of the British Institute of Mathematics and its application. She works on the design of fast algorithms for simulation of complex systems and PDEs, with the focus the latest year on wave propagation problem. Together with her collaborators, she was the recipient of the Bull Joseph Fourier Prize for her innovative work. She co-authored a reference work on domain decomposition method published by Sessao in 2015. She is a member of editorial board of Science Journal of Scientific Computing and of the Scientific Committee of International Conference on the Domain Decomposition. So she's a great specialist in numerical analysis and computational domain. Today she will speak about the fast solution method for wave propagation problems from classical domain decomposition solvers to learning. So thank you very much, Victorita, and you can start.
Okay, so thanks a lot for having me here and for this nice introduction. So I will present my work with a lot of collaborators that you see here that I did in the past 5 years or so. And I'll split my work, my presentation into 3 parts. So all these 3 parts are standalone. So hopefully it will make things easier for you to follow. The only common denominator are wave propagation problems. So let me start with the part 1, which is about what are the best solvers for Helmholtz equation. So what I'm mainly interested in is to solve problems in heterogeneous media as they arise, for example, in medical imaging or geophysical imaging. So in both cases, you will need to reconstruct the unknown properties of the medium. For example, here is the permittivity in the case of medical imaging, or just the propagation speed in case of geophysical imaging. So in both cases, we need to solve an inverse problem. So solving an inverse problem, that means you have an optimization algorithm, and inside the optimization algorithm, you need to solve repeatedly these kind of problems. So my purpose is to have a holistic approach. That means propose a combination of discretization and solvers in frequency domain for these kind of problems. So let me take a pointer if I can. So, okay. So what is the Helmholtz equation? So probably you know, it's also known as time harmonic wave equation. So this comes from a scalar wave equation where c is the propagation speed, where we suppose that, for example, the right-hand side, it's monochromatic. That means has this dependency on time. So we can also prove that the solution is also monochromatic. So we can transform this scalar wave propagation scalar wave equation into this Helmholtz equation when U is now the complex amplitude of the field V. So here we have a few new quantities that appear. For example, omega here is the frequency and is the index of fraction, and K and W is called the wave number. So you see here that if K is small, the Helmholtz equation is just a perturbation Laplace's problem. But otherwise, the solution is highly oscillatory, which creates a lot of mathematical and numerical difficulties. So just to give an idea, so if you have, for example, right-hand side is a point source, your Helmholtz equation, Helmholtz solution will look like this. So you see a lot of oscillations. So how you discretize well this kind of problems? So we have a few issues, and I present them here. So for example, if you discretize it, you want to maximize accuracy, that means the error, approximation error, to be as small as possible. But at the same time, you want to minimize the number of degrees of freedom. And we know from the literature that if you keep h omega constant, h being the discretization mesh size and omega is the frequency, the error will still increase with the frequency omega, which is known as being the pollution error. Now, if you use a finite element discretization, in order to get quasi-optimality, you get this kind of relation. So as a conclusion, that means if you want to discretize well, you need, in order to capture the high frequency solution, since the solution will oscillate as a scale of 1 over omega, you need a very large degrees of freedom. If you don't want to have the pollution effect, as I explained you a bit earlier, you need even a larger number of degrees of freedom. So now the idea how you discretize well. So it means what kind of finite element will you choose in order to maximize accuracy, minimize the number of degrees of freedom. So you will do what you call a dispersion analysis. So that means you measure the ratio between the numerical and physical wave speeds with respect to the number of points per wavelength, which is this quantity. It's the wavelength divided by h with the discretization mesh. So this dispersion analysis looks a bit like this. So here you see two examples of dispersion analysis for finite difference scheme and for finite elements, right? And here what I represent, as I said, the ratio between the propagation speed of physical waves and numerical waves. And you see that the very compact finite difference scheme designed by geophysicists for Helmholtz equation, they are very, very close to one. So that means that we nearly have no dispersion. So we can capture very well the waves. However, if you use the finite elements and we don't do anything special, we use spectral elements and usual finite elements of the degree 2 and 3, you see that these curves that they are far away from 1. So that means we have some dispersion. So how can you read this curve? For example, if you look here, so 0.5, that means it's an inverse number of points per wavelength. If you just choose 4 points per wavelength, your dispersion is really bad because the ratio between the physical and numerical speed, it's very far from 1. So just to say that this dispersion analysis will give you the clue, that means how fine you should discretize the mesh in order to capture the oscillatory solution. So here I'm just trying to give you a numerical example in which I want to compare the finite differences and finite elements and say which one are the best. So if I ask you what are the best finite differences of finite elements, as a mathematician, you always say it's finite elements. We have very nice theory and we can do a lot of amazing things like mesh adaptation, as you see here. So we can clearly have any precision we want. But if you want to reproduce this kind of thing, so you see that it's just a trench of subsurface, and you use finite elements and finite differences, and you just want to measure the error here, you see that the difference between the number of degrees of freedom is quite important. So that means you need twice as much number of degrees of freedom in million than the finite differences in order to get the same accuracy. So for now, I just told you a part of the story. So that means how to discretize well our problem. So at least for this kind of configurations, you see that the finite differences, they perform very, very well. So now let's suppose that you have discretized the Helmholtz problem by some discretization method, finite elements or finite differences. You end up with a linear system, AU equal B. So this linear system is symmetric but indefinite or maybe non-Hermitian. And what is worse, that means the size of this linear system will grow more than linearly with the frequency and with the space dimension here. Okay, when repeats the degree of the polynomial degree in the finite element, so this kind of helps in getting a good size of the system. So this will increase very quickly, and the matrix is arbitrarily conditioned. So if you want to solve this, so how big is this system? So it's hundreds of million unknowns. I want a solution of this linear system in optimal time with a solver that has good parallel properties and is also robust with respect to the heterogeneity. So this is my holy grail. So now what should I do? So you say that it's very easy. If I have this linear system, I just apply A/B, right? You have MATLAB, you have a lot of libraries, so I just use direct solvers. You have a lot of direct library here, yeah? Or I can use iterative solvers, yeah? The problem is they all have flaws. So direct solvers, they are limited in memory and parallel properties, and iterative methods, they are not very robust. So here, I want to give you, let's say, a picture of complexity and memory issues for direct solver. So this is a very simplistic one. If you study numerical analysis in bachelor course, I don't know, year 2 or year 3, you learn this kind of thing, that if you want to perform Gauss elimination of this dense matrix, this is the complexity. Okay. Now, obviously, the matrices that we get here are not dense, so it's they have a band structure, they are sparse, so you can lower the complexity, but still, supposing that you, for example, you have n is a few hundred million, the complexity is very high. So now the idea is, what should we do? So then we want to have the best of the two worlds. I mean, the best of the direct solvers and iterative solvers. And these are the methods I've been working on for years, and they are domain decomposition methods. Okay, so now let's forget about Helmholtz for a few minutes. So you just want to solve the linear system A equal B. And you want to solve it by iterative method. By iterative method is not robust, so you want to apply it a preconditioner. A preconditioner, it's an approximate inverse to the matrix A in order to make the solution of the linear system faster. So how do I build this preconditioner? So don't look, at the formulas too much. The preconditioner is inspired by the decomposition of the computational domain. So you just decompose it into subdomain which overlap. Each subdomain has their own matrix, discretization matrix, a boundary value problem. Then you have some restriction extension operators. So you go from global to local, and you have, a preconditioner for free. That means an approximate inverse to your matrix A. So this is a very good thing. The only thing is that if you increase the number of, domains, this is not enough. Why is not enough? Because imagine that you have the right-hand side, that means the here B, that comes from this point source, which lies in one domain. In order to fill the effect of this point source 100 domains away, it will take more time if you have more domains. So that means the problem is still not robust. So you need to do at the second level, a coarse information. So in order to make it robust, as I said, you add a second level, this coarse information. So this coarse information is embedded. I mean, I can do, I have variational expression of all this kind of preconditioner, but I have chosen the language of numerical linear algebra. I thought it's easier to understand. So this second level is encoded is matrix Z. So this matrix Z, it's a thin and long matrix. So that means it has a lot of rows, but not many columns. So that means if you do this kind of computation, this will be a small matrix. Yeah, this is a coarse information. So that means this matrix M0, it's very easy to invert. It's a small one. So now it's a bit mysterious. What is this matrix Z, right? And there are a lot of different options. I just present one and probably skip the more sophisticated ones, but one is very easy to understand. I think you probably heard about maybe multigrid, multigrid methods. What does it mean, a coarse grid? A coarse grid is simply, if you look at this mesh, this is what I call a fine mesh, it's a coarse mesh, okay? So between the fine mesh and coarse mesh, you have an interpolation matrix in the finite element sense. So this interpolation matrix, the transpose of it will create this matrix which is thin and long. And in fact, the coarse matrix is simply the stiffness matrix or Galerkin projection on the coarse grid. This is probably the easiest thing to understand. This is not new, of course. For Laplace problem, it works very well, but it's rather new for Helmholtz because here we have extra difficulties, as I explained, because of the indefiniteness of the problem. So if you think it's obvious, it was not, because in order to produce a theory for this kind of problems, we needed to work on the Helmholtz equation with the shift, some damped Helmholtz problem. And if you work on the shifted problem, then we can prove some robustness under a certain number of assumptions, which are very, very strong. Okay, so here I underline a very, very important key problem here. So that means if I do this kind of preconditioning, so that means approximate inverse, I want to solve this system in a robust manner. And robustness with respect to the number of domains that I have here, but also robustness with respect to the wave number. So that means that if I have something which is more and more oscillatory, I won't have a problem which is very, very difficult to solve. Okay, so now I just keep this part, but I just tell you the story. So I mean, I don't look at the formula, but just to say that I can build more sophisticated ways to improve the robustness. So that means I can enrich this matrix Z with some spectral information. So this is the whole world, these spectral core spaces, in order to achieve, better performance. So now to finish up this part, so this is what I mean, there are far more things that I learned, of course, but here I just want to give you a summary of the things that work for Helmholtz. So maybe you don't recognize this, but these are called benchmark test cases. So it means there are test cases which are recognized in the community and on which all the Helmholtz solvers are tested because they have different kind of difficulties. So you see, all the problems that you see here are high frequency. So high frequency doesn't mean necessarily that K is high from my Helmholtz, but that you have many, many oscillations in the domains. Yeah, so especially this one, it's very high frequency. So this is a high frequency problem, it's a high frequency problem, and this is a three-dimensional high frequency problem. So these are benchmark things. So you can test, all the methods, you should test them on this, in the first place. So by testing on this thing, we concluded that at the end of the day, this grid core space geometrical grid is the best. Even if we do something sophisticated, it won't work. I mean, it works in some cases, but not on the others. Yeah. So this is this first part. And yeah, some conclusions. So we can do a bit more. I don't have time, but I can, share if you're interested. With this kind of thing, we push this further, this grid core space, and we did larger scale computation for geophysics. So now we have a tool that works very well as a forward engine for full waveform inversion for three-dimensional case. Okay, so there are a lot of openings. So we are working on more theoretical aspects to understand how these methods work, and also computational in order to do a bit more physics and yes, so we obtain some very good results in a very more sophisticated test case. So this was the part on Helmholtz. So I move on to the next part, which is, as I said, different from the first one, but a bit in the same spirit. And I want to tell you a few things about the Maxwell, my work on Maxwell. Yeah, so Maxwell's equation. So here I put just some pictures. Maxwell was a Scottish mathematician. So here I put a picture from Russ at Edinburgh. Here are some, manuscripts for from Maxwell since when he was a teenager, he was already doing mathematics. So here is a statue in Edinburgh and also plaque with his equations. So now that you see, these are Maxwell's equations. So I'm interested in Maxwell's equation in a very particular form because I want to study what I call low frequency applications. So what does mean low frequency? So low frequency, if you look at this application, this problem, the problem is not that oscillatory. So that means it's closer to something which is a stationary thing, right? But the problem with this low frequency problem, they are nearly singular. So that means, imagine here you have only this omega, it goes to 0. If I didn't have these terms here, the problem will be near singular. So in order to treat these kind of problems, we use a mixed form. So here you mix form, you just add a artificial variable p, and you solve the mixed form in order to avoid this. And when you solve Maxwell mixed form, after discretization, you end up with a saddle point kind of problem, okay? So the matrix that you have here is symmetric but indefinite. And also you have here, I mean, you know if you're doing, PDEs and more involved stuff, that you have here a curl operator. So the kernel of this curl operator is the gradient of all H1 functions. So at the matrix level, the kernel of this matrix K is very large, okay? So that means it's problematic to solve this, even if the problem is almost positive definite. So what we do, usually, it's we use what you call a block preconditioner. So in order to precondition this, you use the positive counterpart of this. You just make it positive by adding to K some gamma times the mass matrix. So now you have a fully, positive problem. So then you said, okay, so this Maxwell in low frequency form, in fact, it can be discretized by a positive Maxwell. So then if it's a positive Maxwell, then it's very easy to solve because there is always already a very good preconditioner out there. It's called AMS. It's considered to be one of the major breakthroughs in 2008 in the Department of Energy report. So that means we already have a very good solver for this one. So now in this work, we want to prove that we found something better, or at least we found some situation where this preconditioner breaks and this our method does not break on this problem. Good. So now just to put some mathematics in it. So just to say, how do I solve this? And some abstract framework, which is very adapted for this kind of problem, is called a fictitious space lemma. It's a result from 1991. And I explain it in an abstract way, and then I apply it to my problem. So let's suppose that you have some Hilbert spaces in HD and so two symmetric positive bilinear forms A and B defined on these Hilbert spaces. And suppose that you also have a surjective linear operator between these Hilbert spaces and also these two inequality that hold some continuity between A and B with continuity constant and stable decomposition. So this is an inverse inequality between A and B, right? So how we can interpret this A and B? In fact, A it's the bilinear form corresponding to the problem I want to solve, and B it's the bilinear form corresponding to the preconditioner, which lives on some kind of product space, but we'll see that later on. So this fictitious space lemma says that if these assumptions are verified, then you have this spectral estimate. So what does it mean? If you look a bit closer at this red part, that means we precondition A by this operator, R being the restriction operator, B is the preconditioner. And then you have this estimate with the constant C, R, and CT. So in other words, the spectral condition number of this preconditioned operator is bounded by the ratio of these two constants, okay? So it looks like a very nice result and quite general. And we can put literally all the methods that we have here in this framework. So now again, I mean, you need to take a leap of faith because I don't expect you to go through all these notations, but I want to show you how I can apply this to my Maxwell problem. Okay. So as I explained you before, I have a huge kernel of the matrix K. I just go one back here. So matrix K is a discretization of the curl operator. So the kernel of the curl operator is the gradient of both H1 function. So that means the kernel of K will be the discrete counterpart of this, so discretization of the gradients of all H1 function. So that means I have a certain number of vectors in the kernel that I already know. So that means I use these vectors to add them in the core space in order to improve the robustness. Yeah, so this is the general idea. And then I put all this in this fictitious space lemma machinery, and then I get some kind of robustness here with some better constant that I had before. Yeah, so this is the general idea. Then I can obviously improve on this, and I said, okay, the kernel of K is not enough. I can do some more sophisticated stuff. I add here in the core space some solution of generalized eigenvalue problems. And my core space will be enriched. I apply again the fictitious lemma. I get better constants. So that means my conditioning is even better. So the idea of core spaces, just to explain, is to add enough information which is cheap to compute in order to achieve robustness from the condition number point of view of the precondition operator. Okay, so now I just want to show you some numerical results on this. So I put in competition a few. So here you can relax. You have a few images, nice images, and so you have a certain number of preconditioners. So the state-of-the-art one, the basic one, and those here in colors are the one that we have built. And we want to take two aspects into account. So there are not many images on this one. I try to produce something not only non-convex, but non-trivial topology here. So you have holes across and along. Yeah, so clearly here the properties of exact sequence won't hold anymore, and you don't have the gradients of the H1 function are in the kernel of the curl. Okay, so you just break the hypothesis. Yeah. So you can see here that most of the usual precondition we fail. I put on red all the bad things that could happen. So what are the bad things that could happen? So that means here's the iteration count to achieve convergence. Iteration count, it's also measured at the time. The number of domains, number of degrees of freedom, and you see that they are getting really worse as you increase the number of degrees of freedom, whereas our preconditioner, it works very well. Now I can also try to vary to get the problem as singular as possible. So gamma is the, just going back for 1 second. So gamma is just here. If it's close to 0, the problem is close to being singular. So again, if it's close to being singular, again, the usual methods will break. So now, yeah, I have some other tests, but they're not very important. So I just want to say that, you know, the state-of-the-art preconditioner can break if you just push the limits. It's close to being singular, and the geometry is really like this, which does not correspond to anything physical, but just to say that this is a geometrical assumption that is no longer satisfied in the theory. So this ends my second part. So now I go to the third one, which is a bit completely different. It's a bit we just wanted to explore things and do what everyone does. Just see how we can use neural networks to solve partial differential equations. So here I just put some literature. So this is probably the oldest paper in which the artificial neural networks were mentioned in relation to the solution of ordinary partial differential equations. So this goes back in 1998. It's a paper by Lagaris and collaborators. So what they wanted to do is to solve a general differential equation subject to boundary condition by an optimization problem, which is this one. You should note here that here the psi function, it's what they call a trial function. Xi are some sampling points, and P are some parameters. Okay, so they minimize on this, and they hope to solve this kind of problem. So you see that this is not a neural network yet, it is just a trial function. So what is the trial function? The trial function is built in this way. It's composed of some function that satisfies the boundary conditions and some function f applied to a neural network with parameters p that not satisfy the boundary condition. So in other words, they wanted to, for this trial function, to enforce in a hard way the boundary condition. So from the conclusion of the paper, so they said the success of this method can be attributed to 2 factors. The first one is the employment of neural networks that are excellent function approximator, and the second is the form of the trial solution that satisfy by construction of boundary conditions. So this is the first paper in which PDEs were solved by neural networks. As you see, it's quite old. So if you want to sketch their approach, so this is a feed-forward neural network with some inputs, internal layer, activation function. This is the output. And the output, you put it in this trial function in order to satisfy the boundary condition, and then you minimize this quantity here, okay? Now, it's probably this is very, very famous. Everyone knows about the PINs 2019. In fact, they are just to revisit the approach from Lagaris 1998. And they call this method physics-informed neural networks. So let me explain what is the difference. It's very similar to the previous one. The only difference is that they add an extra term where they penalize the boundary condition, initial condition. Yeah, so you have the Lagaris function to minimize, and then you add some penalization with the data. Okay, so what we call data can be initial condition, boundary condition, or simply data. So if we are to summarize this, it's the input, it's x and t, internal layers, and the solution u, it's plugged into the loss function and minimize. What do we know about this? So obviously there is a huge literature, a lot of things which are probably not worth mentioning, but a lot of numerical works. But here I just try to summarize a few things which are theoretical. So you have here a result from 2022. Where they estimate what they call the generalization error of the training of neural networks. So the generalization error, it's bounded by what they call the training error. and some approximation error here, because you approximate, use some quadratures, right? So here, these two constants here depend on the PD, on the quadrature, and you see with the quadrature you can control this term here. That means if you choose a high precision and a big N and so on, this goes to 0, but you cannot control this training. That means if you optimize the loss function, it's very difficult to control this. So they said, okay, as long as the pin is trained well, it generalizes well, which that means, all the details, nasty details are there. The problem is, even if you train well or try to train well, the neural networks suffer from spectral bias or scaling issues. So let me explain you spectral bias in 2 words. So let's suppose that you want to reconstruct a function like this. You see it has several frequencies, have lower frequencies, medium, and higher one, right? Suppose that you want to reconstruct this by training neural networks. And you see that if you wait, for example, say 100 iterations, you have built only the lower frequency. 1,000 iterations a bit more, and you need to wait 80,000 iterations in order to reconstruct the whole function. So this is called a spectral bias. That means the neural networks learn faster the lower frequency than the higher frequency, if at all, because you're not sure that they will learn. So that means training may not be sufficient to reduce the loss, even if you take the large number of iteration. So, and also if you want to capture this multi-scale feature, you need very, very large neural networks. So what is our solution? I mean, the solution proposed is the following. So again, let me give you a few more pictures so you can understand a bit better what this spectral bias means. Let's take a very simple ULI. You see, it's a very, very easy one. But you see here that the bigger the omega, the more oscillatory the solution is, right? So if omega is small, for example, 1, here it's enough to take a very simple network in order to train it, 2 layers and 16 hidden units. So you have 300 parameters. You can already reconstruct this one, okay? But if you take the same configuration and if you increase omega to 15, you see that the solution is completely rubbish here. So you need to increase the network in order to get a bit more, even more, right? So even if you put 60,000 parameters, your solution is still not satisfactory. And if you look at these training loss curves, you see that the first one, it goes to 0, sort of, because it's 10 minus 4. But the other ones, the decrease of the loss is very bad. So now what is the idea? So the idea is the following. So let's do something else. You see the higher frequencies are in fact the lower frequency is to split the domains in smaller pieces. So for example, what I want to do here now is to train locally. I want to localize the training by this kind of window functions. I decompose my domain in overlapping domains. I generate locally the collocation points. And then I train, some global function, which is localized with these window functions. Okay, so now let me explain you how it works. So you probably heard about the gradient descent. So the gradient descent method, you just want to, for example, to minimize this loss function, which contains the PD operator, and contains also some parameters theta. So the gradient descent, that means you start from the initial guess and you apply something like this, yeah, a iterative method. What is the difference in what we are doing? We just train locally, yeah, by just freezing. We perform a certain number of gradient descent iteration on just some part of the parameter that correspond to the local domain. Yeah, so it's some kind of Jacobi-like problem. You just freeze everyone else, and you just go on gradient descent on one parameter. And then you communicate this, and then you go back to this. Yeah. So by doing that, you ensure that the higher frequency will become, if you just cut this here, for example, this is a higher frequency problem. If you cut it here, the higher frequency at the global level will become lower frequency at the local level. Okay. So by doing this kind of localized training, then you can get very good results and beat the standard method. Okay, so now let me show you how it works. So I can, build more levels. So see, for example, I have a very simple boundary value problem. I increase the number of domains. I have more levels, and you can, you can get a almost a prescribed accuracy with by training on neural networks. Which is, again, I agree, it's not enough, but we can, train reasonably well without with a lot less of spectral bias. Now we can do also multi-level, so we can have a multi-level architecture. For example, we have a level one domain, 2 domains, 4, and so on, right? So you can do this multi-level training. And again, by multi-level training, you can reconstruct also solutions like this. For example, you have something that has a lot of different frequency, a lot of features. And if you add enough levels, you can capture all the features in this solution. Okay, so here it's again Laplace problem with multi-level, and you see that you can, if you put enough levels, you can reconstruct it. If you don't put enough levels, even if you put a high capacity in the neural network, it won't work. So I want to just wrap up here. So I'm close to the end. So I just want to show you that, I'm primarily interested in the Helmholtz problem. And what I did before with multi-level training is just to warm up and to understand how I can do something more complicated. So this is a Helmholtz problem with a more and more higher frequency. And I try to do my multi-level training on it. Obviously, it's not perfect because I can reconstruct up to a certain extent. You see, it's close to the solution, but still it's not as for Laplace problem. So yeah, I just jump onto the conclusions. So this last part is probably something that I'm also continuing to do. So if we try to import these ideas from domain decomposition to the training, we get to this multi-level training, and you have the codes that can be tested here. This multi-level training is very exciting because it's not limited to pins or given architectures, and there are a lot of other things to explore. Okay, so I'm done. So thanks for your attention.
Thank you very much, Victorita, for this very nice talk. So let's ask if there are some questions from the audience. So are there any questions? You can use your microphone and also, yes, the audio is open, so you can use your microphone, also chat. So please.
Mm-hmm.
I have one question just for curiosity.
Yeah.
Yes.
Yeah.
It's only a curiosity. When you were talking about, I think in page 9 or 10 of your presentation, about the example of a course space.
Yeah.
When you were working on that, were you thinking about some specific application in nature or?
Yeah, so this is okay. So the core space is this is for Helmholtz in general. As I said, we apply most of the problems from geophysics.
Oh.
So in geophysics, you have this inverse problem that we don't solve directly, but you have, for example, this kind of thing. This is acoustic approximation of the pressure waves. The model is Helmholtz. Okay. You can also do other kind of approximation. You have elastic approximation. So there are all problems in frequency domain. And they are, very difficult from mathematical point of view as well. So the applications are for Helmholtz, at least from geophysics. Yeah.
So it's in order to try to identify some domain or something, no?
Yeah, exactly. So I mean, the purpose is inverse problems, but in the inverse problems there is a building block, which means you need to solve this kind of problem. Yeah. So you see, you have also this one. This is a 3-dimensional. You see there are different layers with different velocity speeds. So you have different materials. So you want to reconstruct something like this, but we did not go until the reconstruction. Yeah.
Okay.
It can be used for for do something like this. Yeah.
That's interesting application. Thank you, Victorita.
Are there other questions, please? I just have a curiosity about the last part of your talk. So selection of the hyperparameter of the neural network, for example, the learning rate or activation function. So is it important in simulation, or you can use whatever you want?
So there are people that study that. So in this kind of pins thing, you need the activation function that is differentiable. So typically you will avoid the the ReLU or something. So you need something differentiable here. But you have also other version of solving PDEs, like like variational form or this finite neural method, and then you can use other activation function which are just piecewise differentiable, like ReLU and so on. But in this case, you need to differentiate twice, so you need something which is hyperbolic tangent or plane waves or something. But yeah, there are people that study that this activation function is important also for spectral bias and hyperparameters. I don't know. I mean, the learning rate, clearly you can study what would be the optimal learning rate in some cases. Yeah. But yeah, activation function clearly is important. Yeah.
Okay, thank you very much. Are there other questions from the audience? Okay, if not, we thank you again, Victorita. Thank you very much for this wonderful talk. And thank you for being with us. Okay.
Thank you, Anna. Thank you a lot, Professor Victorita Dolean, for your amazing talk.